Hey, come. So welcome to this would be the fourth class of the summer pre-course interactive mathematics with Mathematica. Okay, so let's go ahead and pick up where we left off again. After an introductory remark, a lot of introductory remark about the role of mathematics in class 1, we went to the basic element, the very core element of the mathematical objects, variable, constant, parameters, and whatnot. And then we spent quite a bit of time on Friday on the notion of function and how it produces an output, input, output, and so forth. And then with function, it's not just performing arbitrary calculation. It also requires that you stipulate the domain. In other words, the range of input for which the function or the operation is valid. Okay, and obviously you have you might want to keep in mind is like a function is division, and of course division takes two numbers a and b, but it has a stipulation that b cannot be 0. Okay, so give me any a, give me any b, as long as b is not 0. So in which case the domain of the input of a is real number, right? Negative, continuous, positive, continuous, and 0. But the domain of the second variable is everything but the value 0, because you can't divide things by 0. So that's the concept of a range. Then we kind of finished the class with going back to the natural range of number. So we introduced the concept of natural range of number, in this case, the set, right? And the number can have a finite set of values. So the set can be a finite set is something that you can enumerate, A, B, C, D, E, F, G, okay? Bob, Alice, Dome, Ethel, whatever, okay? But now we're going to deal mostly with number, okay? Eventually we'll be able to capture pictures, persons, even text in numerical domain, and we do that in like machine learning, data analytics class. But right now, let's take ourselves to a set of numbers. And so we talk about finite, okay? So you have a finite number of numbers, finite number of numbers. You can have countably infinite set, meaning infinite numbers of numbers, okay? But you can count them. You can start counting them. You can count the first element, 2 element, 3 element, 4, 5, 6, first, third, fifth, okay? Like even number or odd number or integer, right? You can keep counting. You can't stop because you can't account for all of them. Then you have uncountable infinite set, which can be bounded on both sides, like any number between 0 and 1 can be bounded on one side, like positive number, can be bounded on no side, in other words, unbounded, and that gets back to the real number. That gets back to the real number. But while we are talking about set, okay, we go ahead and talk about set operation. Okay, and that's where I think where we left off. So let's go to our class. Okay, so let me hide this. Let me just hide this on the second screen so it doesn't bother. Again, this is sort of like the outline of my textbook. Okay, we don't need this. Okay, let's go to Mathematica. Now, I trust that all of you have been experimenting a little bit with Mathematica, just throwing in some calculation. Okay. By the way, Well, one thing which I didn't mention was that with Mathematica, you have this thing called Wolfram Alpha. Okay, Wolfram Alpha. Now, if you go to any kind of cell, okay, let me go to an empty notebook. Okay, if you go, again, when you click this, you can enter a few things. By default, it is Mathematica command. So this is the Mathematica expression. Okay, so this is something you can do calculation with, right? Or you can go to free form input, which is a sort of like a natural language version of this. Okay, so say add 1 to 1. Okay, and the machine is trying to interpret that this is what you're trying to do. Okay, is this what you want? Plus, okay, something like that. Okay, so maybe so something like maybe sine of x from pi to 2 pi. Some reason it gave us something more complicated. See? So this would be the mathematical expression you input if you were to do it this way. This would be the free form that you input, and then the Mathematica algorithm, the sort of machine, the AI engine, try to interpret what you wanted to do. Is this what you want to do? And assuming it is, sometimes it gives you a few options if it's not sure. So you click on which one you want, I think. But this one is kind of obvious that you wanted to plot sine, so it gives you the expression. So obviously, this is the expression. See? So once you click it, it just becomes, you look like an expert now because you actually are not talking in free form. Now, another thing you can do, which I haven't shown before, is this thing. It's called Wolfram Alpha. You can think of Wolfram Alpha as sort of like Wikipedia plus Mathematica. Only it doesn't deal with facts in general. It deals with computable facts. Okay, it probably deals with all kinds of facts, but so it's kind of inquiry. Okay, so if you think about it, let's say I want to know what is the population of Thailand. So you can do that with Wikipedia, correct? So let's do that. What is the population of Thailand? Okay. So it's going to search the internet just like that. It's here. First of all, it's giving you a basic descriptive statistic. Most people want to know. If you wanted to know about this number, instead in Wikipedia, you just get some in Google. If you want to Google, you just get this number, right? And if you go to Wikipedia, okay, you have to go to the population section of the Thailand page, okay? Or maybe there's a page of population of different countries, list of countries by population, and then you go to Thailand. Okay, but in this case, it's doing a selective search for you. Okay, so it narrows down. So it works like Google plus Wikipedia plus graphical interface plus something else, which I'm going to show you. So you say, what's the population of Thailand? It finds the intersection of population in Thailand, just like you would in Google. Okay, but instead of just giving you the number, it's sort of like accessing all the information you have about this. So it's a little bit like Wikipedia. Okay, but then it does this preliminary graphical output because most people who, it's sort of like making a guess. If you want to know about population of Thailand, maybe the next question is, well, what was it like before in earlier times? So it gives you this kind of population history automatically without asking. Okay, you can imagine that the first thing you ask is the population of Thailand. Second question would be, has it been growing in the past few years? So this automatically sort of like does that for you. Okay, so this is kind of a machine intelligence guess of what you would like to know that next. Okay, and gives you a little bit of option as well. For example, you can say go to log scale, because sometimes population explode. Like if you were to do this in China, it may go something like that, okay? And so it's better to go to log scale. So you can do all kind of stuff. Long term, so this is a bit short term, this is long term. Again, this is something where, log would make more sense. So you go to log scale, okay? So smooth it out a little bit, okay? In epidemics, like studying pandemic, the spread of pandemic, sometimes we work with log scale. Now, it's giving you additional facts that are related, okay? And it's giving you a whole bunch more. Now, normally, if, as you go down, it sort of like gives you more and more details, okay? But unlike in, say, Wikipedia, where the details are text or description, these are more numerically oriented details, right? Things that has to do with, okay, so maybe you care about male and female population, right? Okay, so 0 and 4, this is a histogram of male on one side. By the way, I think this is called violin plot. Okay, so this is automatic. Now, in some version, I don't know if this version still does it, but in some version, it does make some kind of suggestion as well. But I think you can turn that off or you can turn that on. So instead of giving you all this, it might give you a suggestion of what you want to do, what you wanted to do next. Okay, but I think this version just gives you what it guesses. Okay. So there's some options about how you want to interact. So once you have this, the interesting is, once you have this becomes an object. You can actually assign, say, some variable to this, okay, and then do calculation. And this is something that is very powerful. So let's see. Let's look at COVID cases. Thailand. And so it's guessing you want cumulative, right? You don't want this today, you want cumulative, but it's probably going to give you other number as well. So again, if you did this in Google, you would just get that number, 336,371. Okay, but here it might give you additional information and so forth. So that's that. I thought, okay, oh, there is. It's giving you a plot. It's giving you a comparison with countries. So Thailand is kind of orange compared to red countries. Okay, because at one time we were doing so well, because we kind of took decisive action. But again, as with in a large country, sometimes we can't do decisive action because we have resistance. So we became less decisive over time. And so the case grew. Something like that. Okay, so it's giving you a whole bunch of things. So you can play with this. Again, what you do is you go input. I think there's a shorthand for it as well, like Shift Enter or something like that. I'm not quite sure to get this prompt. So basically, those are the 3 prompts. Okay, and this prompt is just to make a text. Just write down text. Okay. So this is good for documentation. And this is something that for those of you who want to, I guess, especially, I think about 40% of the new coming class are interested in applied digital intelligence. This would be something very useful because a lot of machine learning algorithm in AI or any kind of intelligence application, a lot of applications are written in software, sort of like a shareware in Python. Now, it used to be that you have to work in Python, Jupyter Notebook, and then come back to Mathematica and blah blah blah. Now you're done. You can actually work with Python right here. Okay, so this is both a Jupyter Notebook and Mathematica Notebook. Okay, it's kind of obvious extension because after all, Jupyter Notebook was modeled after Mathematica Notebook. So this is sort of like coming back home, So now with this in one interface or one platform, I can work with Mathematica function. I can access external library that is written in Python. Okay, And presumably, I think, there might be some other language as well, JavaScript or whatnot. But I think right now, I think we just have Python. Yeah. Okay, and this is useful because my team on their execution on project software, again, uses a lot of shareware written in Python. So, right. So let me, I don't need to set this. Okay. Okay, so let's go back to, where are we? Oops. Okay, so where are we? Okay, so we did this, we covered this again. So let me just hide this. We have that. So now, okay. So again, if my set is equal to set of 1, 3, 1, 2, whatever. Okay. The size of my set is the same thing as counting how many elements. Because it's the same thing as counting the number of elements, it's the same thing as the length of this list. So size of my set is equal to length of my set, right? So 4. Okay, so that, however, only works with finite set. Okay, now infinite set, you can't do that because again it's infinite. It's infinite. Okay, so the concept of length of list is so limited, and the concept of number of elements is also limited. So mathematically, they define this concept of cardinality, which is the size of the set. Now, for this, the size of the set is simply the number of elements. Okay, but the cardinality is the size of the set, so it could be infinite. So now we talk about this, an empty set, a set of nothing, right? Maybe a set of people who are alive today who were born in Victorian time, okay? A singleton, maybe the size, the set is the number of people who are alive today who were who took part in World War I. So maybe there's one World War I veteran alive. So that's one. Finite, again, that's what we're talking about. Countably infinite, bounded, okay? So bounded can be something like between -1 and 5, okay? In this case, how do you read this? From -1, any number from -1 to 4, including 4, but not including -1. So this is kind of open bracket, okay? Open bracket, because open bracket means up to, but not including, or down to. Okay, so now we're talking about set operation, and this is where something that it's just a reminder of what you did when you did the Venn diagram. You remember that when you were very young? Venn diagram, right? Venn diagram. So a Venn diagram, a complement is whatever is not A. Okay, so what is a complement? Complement of 1, 2. Yeah, what's that? What's a complement with this? Is equal to real number, set of real number, not including 1, 3, 4, 5. As simple as that. Okay. Intersection. Well, again, all of this. The reason it's called set operation is that the object that you operate on is not the element. It is the set. So you get set and you produce set. You take one set here, you take one set here, take one set A, and produce another set of A, complement. Okay. Now, what's intersection? Intersection, you don't take one set. Okay. Intersection, you take two sets. Take a set A and a set B and produce another set called A intersect B. And that set contains all the common elements. The union means it's either in A or B, okay, and so forth. And this is something, this is O. This is something you've done. Now, symmetric difference is slightly different, okay? Symmetric difference. What's symmetric difference? It's in A or B, but not both, okay? So let's see, let's go to Wolfram Alpha query. What is symmetric difference? Okay. Now, in this case, notice this is a concept, right? So it looks up just like you would do with Google. It gives you a definition. Element belong to A and B, but not both. But more interestingly, it gives you a mathematical expression for it. So it's saying take the complement of this, take the complement of this, okay, and union them or something like that. Okay, so complement, difference, and it's giving you related item. Okay, it's giving you related item, okay, and blah blah blah, and so forth. So it's giving you how you would define symmetric difference. Okay, in fact, I don't know if it's a built-in function. Oh, it's not a built-in function. Okay, if it's a built-in function, it will give you a built-in function as well. So there. Now, another thing that you have not learned, you may have learned, is a power set. Power set is slightly different. You're producing set, but you are producing set of all subset. Okay. So let's use Wolfram Alpha. What's a power set? Okay. Assuming, this is very nice. It's being kind, right? It's saying that assuming this is what you check your understanding. Is that what you want? Okay. The power set is, okay, sometimes called power set without space. It is set of all subset. Now, I think we have to recall the definition of subset. Subset means that if A is if A is subset of B, then an element in A must also be in B. In the bracket, parenthetically, not necessarily the other way around. Okay? Now, there's another definition I might as well add. If A is a strict subset of B, then, okay, not only this, not only an element in A must also be, but also there must be some element, maybe just one, in A that is not in, in B that is not in A. Okay? So my question is, okay, is 1, 2, 1, 3, 4 is a subset of 1, 3, 4, 5? Yes. Is it also a strict subset? Yes. Now, let me write this again, and I just say Okay, what about this? The first answer is yes. The second answer is no. Because all elements in the ladder is also in the former. Okay? So just remember this picture. Okay? Now, obviously, if A is a subset of B, then cardinality of A as a consequence, okay? Now, as a consequence, cardinality of A is less than equal to cardinality of B, right? If it's strict subset, then cardinality of A is less than cardinality of B. And that's obvious from just counting. Okay. Notice when you write in text, Mathematica doesn't automatically make a correction. It doesn't know this is just a nice picture that you want to draw, like a smiley face or a real mathematical symbol. But if you use something like this, like this normal, less than, equal to, it would automatically convert it into less than equal to. Okay, fine. So that's what the power set is. Okay. By the way, how big is the power set? Let's do a little experiment. Okay. Okay. Now, if the set is okay, let's use the same example here. If this is an oops, sorry, power set of 1, 3, and 4 is equal to set of set. So there's an empty set. There's a set of singleton. There's a set of singleton. Right? And there's also a set of pair. Okay. And there's a set of the thing itself, right? Because 1, 3, 4 is also a subset. So power set is a set of all possible subsets. Now, this set has 3 elements. The power set has how many elements? 1, 2, 3, 4, 5, 6, 7, 8. The power set cardinality of power set of A is equal to 2 to the power cardinality of set A. So this set cardinality is 3. The cardinality of power set is 8. 2 to the power 3 is 8. Why? Because in order to enumerate the subset, you have to ask yourself, okay, we can include 1 or not. We can include 3 or not. We can include 4 or not. So this is equivalent to doing this. This one is not including 1, not include 3, not include 4. What about this? Include 1, but not 3, not 4. You can see that? So it's a binary choice. Okay? Each element has the option to be there or not be there. Has an option to be there or not be there. So imagine this is like a class reunion. Okay? A class reunion. You have a class of 3 people, and you say, well, let's have a class reunion at a gala or something, like a party. Okay? each one of them has an option to be there or not be there. Maybe no, it's not a very friendly class, so nobody wants to be there. Maybe one person wants to be there. Maybe this other person wants to be there. Maybe two person want to be there. Two person, maybe everyone wants to be there. Okay, so this is the number of configuration. This is called power set. Okay, this is called power set. Now, there's another thing called sigma algebra, which I guarantee that none of you have ever heard of. Yeah, you've heard of sigma, you've heard of algebra, but you haven't heard of sigma algebra. This is something I will not cover here. Okay, sigma algebra is a subset of power set with special properties. Okay, I'll talk about it later when we have time, but I think we probably won't have that luxury of time. But it shows up in financial engineering. Okay, it shows up in financial engineering because if you think about it, okay, I'll talk a little bit about this. Okay, this is all the possibilities. Okay, nobody shows up. The first student show up, the third student show up, the fourth student show up, first and third shows up, and so forth, right? Well, what I want to do is a sigma algebra of 1, 3, 4. Okay. First of all, start off like this. Start off like this. So it must allow for nobody to be there. It must allow for all of them to be there. So this is a valid sigma algebra. Okay. And this is another sigma algebra. It's saying that if 1 is there, let's say I pick 3. If 1 is there, if 3 is there, the complement has to be there as well. Not only has complement has to be there, the union has to be there as well. The union is already here. Okay. Anybody knows why we want to do this? Well, if we did this, we can define this as event, a complement of event, a union of these two events, which happen to be everybody. And so if you assign probability to each event, you cover all the events. So in financial engineering, you have to create what's called financial options. Okay, so it's an option price of stock. So you have a stock price, and you have a in finance. Let me just take a segue here. In finance, you have stock price. S. You have option on stock price O, which is the right to buy S at a predetermined price on a given date in the future. Okay, so this is good, right? Because S can go up and S can go down. Okay, but if S goes up, right, it can become expensive. Okay, so if you have this option, you have the right to buy S at some fixed price in the future. And if that price in the future is higher, you are already doing better than everybody else. Okay, so let's say you have an option price on iPhone 20. Okay, so at that time, I don't know how expensive iPhone 20 is going to be, but you know, at that time, you have the right to buy iPhone 20 at a fixed price. Okay, maybe 20,000 baht or something. Now, if at that time iPhone is worth iPhone 20 is cheaper than that, then you just go buy iPhone for market price. But if iPhone on the market is higher than the price that you can get, you obviously use this. So this is good. This is called an option. Well, the idea here is that option is defined, is linked to this, and it's linked to some kind of probabilistic mechanism. So S here can go up, can do nothing, can go up, and if it can go up, it can also not go up, right? Remember the complement of 3 and 1/4, same kind of concept. And if you have probability of this, probability of this, probability of this, and so on, you can model option price. Okay, so you can see that this power set, which is probably something that was taught to you when you were in 5th grade, maybe later, some tweaked version of it called sigma algebra ends up being the tools of the trade of financial engineers, who at some time ago used to be the highest paid financial professional. I don't know, maybe data scientists are now, but 5-10 years ago, if you walk into a bank, unless you're the CEO or the C-suite, in terms of specialist skill, financial engineers are the highest paid in the bank or any kind of financial institution. Anyway, so I kind of like I do. Okay, so I give you a little bit of sidetrack, so it gives you the power of mathematics as well. So now let's go to logic. Okay. Logic. Well, another step forward from operations. Okay. Another step upward. In other words, let's go back to a set of objects, not set of numbers. Okay, set of objects. Okay, set of objects. Set of and set of people over 50, right? So if you do the intersection of this, what do you get? Intersection is equal to min over 50, right? Something like that, right? Intersection. Now, a logic is something like this. Do you belong to this? Okay, and you can do yes or no. Okay, do you belong to set of people over this? Yes and no. Okay, now you can do something like, okay, screening. So let's say that if you are men over 50, then you're likely to have, say, balding. Okay, I don't know. Okay, okay, balding or something like that. So maybe let's make it more realistic. 70, 80. Okay, 70. Okay, likely to have balding. It's saying that the question 1 and question 2 being true, In other words, if you are both man, male, as well as over 70, you're true on both questions, then you are also true here. So instead of referring to the set, you can just work directly on this. True and true implies true. Okay, except this true maybe apply to something else, right? This is true for whether or not you are male or female. This is true or whether or not you're over 70. This is true about something else, about the likelihood of being born. But the power of mathematics is that doesn't really care what the narrative underlying it. It operates something like this. So for some kind of balding screening, you might do that. For heart attack, it might be something like true or, okay, it may be some other question 3 or question 4. True. So for example, question 3 could be something like, do you work in a factory? Question 4 would be, do you smoke? And this thing could be likelihood of having cancer, okay, lung cancer. So in this case, it's not and. You don't have to be smoking in the factory. You can be smoking or in the factory or both. So that's what this kind of thing allows you to do. So this is kind of logic, okay? And maybe I should have listed Boolean logic first. So this is what's called Boolean logic, because Boolean comes from this guy. And in this case, let me actually go to a proper Wikipedia, Boole, because I think you're going to get nicer picture. George Boole. Okay, it's this guy, okay? Well, anyway, the number system that he works with is true or false. So either true or false, X can be true or false, or alternatively, 0, 1, okay? And the idea here is that you have true and true produces true. So you have what's called truth table, okay? Maybe I just might as well do this. Truth, Boolean. Remember the true and false here? Okay, this looks like that. True and true. Oops, sorry. Logical true, right? Oh, this is predicate, sorry. Binary, see? And true and true makes true. True and false makes false. But if you go true or false, you get true. Okay? So these are all the different sort of like maybe cancer screening or medical logic. Okay? In fact, in the old days, before artificial intelligence creeps into medical diagnostics work by something like this. If you have this symptom and that symptom, or the other one, then you are blah, blah, blah. Okay? So this used to be the bulk of medical diagnostic used to be written in this form, basically. Now, there are two more logic that I'm not going to cover. The predicate is like, if you look at, well, this is the sort of logic that you learn from the Greek, the ancient Greek, you know, sort of like if, okay, something like all dogs love their owners. Okay, 50 is a dog owned by Shelley. Okay, so these are the predicates. The conclusion is therefore 50 must love Shelley. That's the whole thing. Okay, so this is kind of logic. Works a lot in semantics. Fuzzy logic is an extension of Boolean logic, where instead of you are either true or false, you can be almost true, almost false. Okay? For example, with Boolean logic, it makes sense for you to do something like this. Is Bob here? True or false? Okay? So 0 and 1, right? How about if I ask another question? Is Bob paying attention in class? Well, it's not 100% thing, isn't it? So how about something like Bob's attention is a fuzzy number between 0 and 1. Okay, 0 means he's actually asleep. 1 means he's sitting in front and, you know, paying every attention, all the attention to every single word I say. And, you know, most students could be something like 0.6, 0.7, whatever. Okay, so the idea is that with true or false, we have this kind of truth table. Okay, with fuzzy logic, you don't have true or false, you have numbers. How can you do something like 0.7 and 0.89? Okay, so you need a lot of mathematics, or not a lot actually, quite simple. So this becomes a system of similar to Boolean, but more powerful because it can work with things that are not hard and fast, black and white. Okay, another example is, of course, is the room temperature over, say, 25 degrees Celsius. Okay, you can answer that with true or false, right? Okay, now, what about this? What about another one? Is the room hot? Okay, you can't say hot or not hot. Okay, let's say you define something like below 25, sorry, above 25, and it's considered hot. The point is, can you say something like 24.9 is cool, and then 25.1 is hot? Would you say that? No, it's not that sharp, right? So there's a curve. There's a curve between hot and not hot. And that curve may look something like this. See? See? So this is how hot it is, right? Now with Boolean logic, it's cool, it's hot. With fuzzy logic, you have some number between. So if you say something like 24.9, you kind of like crossing the boundary. You're crossing over to the hot territory, but you're not there. Okay, so this is called fuzzy logic. And if you go home right now, well, not go home right now, you are home right now. Okay, this evening, go help your dad, your mom in the kitchen. You will see that the regulator in a rice cooker use fuzzy function. Okay, it might say something in the manual or in there. Okay, so that's fuzzy logic. You'll be able to work with that. Okay, so Boolean logic, well, this is and not. Okay, this is basically the truth table. The truth table. Okay, so truth table basically or not. Okay, so if I say something like do something like true or false, okay, and so and true and false, what do you think you're gonna get? You're gonna get false. Now, in Mathematica, you can also write something like this: true and oops, sorry. Oops. That's and. Okay, this is symbol for or. So this is so I give you this, you can play with it. Okay, so you can imagine that even with this, you can already build an app for a home diagnostic test. You know, like temperature over this. Okay, so something like cough or cannot taste anything, and been to public. scattering, okay, and the production is true. You should go get COVID test, something like that. Yeah, so you can take the sort of Boolean approach to that. Okay, now, so with this, okay, I'm going to go to, let's say we have all the elements and the basic operation. Okay, so again, what do you have? What are the basic elements? Elements are numbers. Okay, okay, the basic elements are numbers, and if you put them together, then they become element of set. So you work with set, you work with number, you work with set. With number, what do you do with them? You check binary relation and you do binary operation. Okay. With set, you also have set operations. You also have set operations. So you play with number, you work with number, you use binary relationship to check. You have binary operation. Same with set. What do you do with set? Well, you can assess the cardinality. You can perform set operation, union, and so forth. Now, when you check whether or not something is in a set, you get something like true or false. Well, true or false can be, you can work with true or false, right? True and true is true. True and false is false. So that becomes a form of logic. But instead of just giving you that Boolean logic, I might as well introduce you to two more forms of logic: predicate logic and fuzzy logic. Okay, predicate logic, chances are you probably will not use that quite a lot unless you go into legal profession. Legal profession, predicate logic is the primary way of thinking. In medical diagnostic, in the old days, Boolean logic is the way of thinking. In most analysis, fuzzy logic, not in the direct form, but in the form of machine learning, is the way of thinking in most problems nowadays. Okay, so you may not use formalism or fuzzy mathematics, but when you go to things like, is this a cat or dog, right? There isn't a, yes, cat for sure, yes, dog for sure, because of like a fuzzy, literally fuzzy, okay? So you have a fuzzy number that represents catness or dogness of a picture, and that's what neural network or machine learning algorithm tells you, okay? Now, sometimes you don't interpret in terms of fuzziness, you interpret in terms of probability, okay? So so fuzzy is also another way of thinking of uncertainty. Probability is another way. Okay, good. So when you get something like a classifier, okay, a classifier looks at the picture. It's a little bit, it's a bit dark. You can't make sure. You say, is it a cat or is it a dog? Okay, and the computer gives you numbers something like 0.9 cat. You can kind of interpret it as 1 being Boolean cat, 0.9 being fuzzy cat. So it's a degree of uncertainty. Or you can interpret it as the computer thinks it's a cat with probability 0.9. Okay, so sometimes you work with fuzzy, sometimes you work with probability. But fuzzy is very nice because it does have this kind of logic system, whereas probability doesn't work with a logic operator. It works with something else. Good. Okay, so types only introduce logic operation only for this. Okay, there's that. I haven't given you any operation on this, and I certainly haven't given you any operation on this. So this is only on Boolean. So maybe I should have put Boolean first. But anyway, predicate should be first because I think it's more historically the most prominent. Okay, now we are going to is equation, variable, function, series, and sequence. Now, what I did last week was a little bit about function already, about variables already, okay? But now we're going to talk about how we annotate, let's say, how we write. So the first thing you think about is in mathematics, even though mathematics also deals with inequalities and whatnot, and expression and series and all kind of stuff. The most fundamental thing when you think of, okay, in mathematics, sort of like the most basic verb, okay? It's like in English, the most basic verb is, right? To be. To be is the most basic way of creating a sentence. I am Bob. I am Alice. Okay. I am hungry. Okay. So is, am, are, to be, not to be, is the most basic way of making a sentence. Well, the most basic way of making mathematical sentence is an equation. Okay. It's the most ubiquitous. And the equation tells you in this form. Left-hand side equal to right-hand side. Left-hand side equal to right-hand side. Okay. This is a statement. Okay. Now, recall that in Mathematica, left-hand side equal to right-hand side is not a statement. It is anybody? It's a command. It's an operation. Okay. Okay. In Mathematica, what this does, sets value of left-hand side to that of the right-hand side. Okay. What else? Left-hand side equal right-hand side. Now this is closer to a statement, but this is not quite a statement. It is an assertion. So it is a statement, but you know when you say a statement, you usually assume, okay? If you're making a statement, assume it's true, okay? Because not true means lying, and lying is bad, okay? So in mathematics, when you see something like this on a page, it's a statement that is taken as true, okay? So when I see in a mathematical paper, I say x is equal, y is equal to x plus 5. I have to take this as true. This is not a trick, okay? Now, in Mathematica, y is equal to x plus 5 is an assignment. Y equal to x plus 5 is an assertion, meaning this is a Boolean. Okay. Hence, a Boolean expression. Okay. So it could be true, it could be false. Okay. So if I say right-hand side is equal to 4, left-hand side equal to right-hand side, that simply assign the value 4. So if I come back and ask left-hand side equal to right-hand side, now it's going to give you true. Okay. But if I just say left-hand side is equal to right-hand side plus 1, this is no longer true. It's false. Okay. So this is a checking, a Boolean check. Okay. This is an assignment. Okay. Right. Because in Mathematica, as in programming, you have to tell the computer. So is this the same thing as a statement? No, it is a statement only because you made it so. So this looks like a statement in mathematics. The mathematics says this, right? This is a statement. It must be true. In Mathematica, it is also true. It is true because you just made it. The minute you type this, the minute you type this, okay, you ask, and it's true because you just assignment. You just made the assignment. Okay, so it's not. So in programming, it's more than a statement, right? It becomes a statement because you just made it so. So it's a command. So be very careful about this. Now, equation is the most fundamental way of making a statement. Okay, it's a sentence. Okay, who does what to who in mathematics is saying left hand side is this, and henceforth equal to this is a more like a programming interpretation. But actually in mathematics, it is this equal to. Okay. Now, variables are placeholders, okay? No intrinsic value, and you hold it, okay? And maybe I should add right here the definition of variable versus a parameter and so forth. Now, a function, we did that, okay? Okay. Now, in the I'm not going to cover this. This is just simply means one operation or many operation, but I'll go to this. A pure function, or this is also a little bit tricky. I'm not going to cover this as well. The distinction here is a little bit tricky, but what you need to know is that the distinction between built-in and user-defined. So built-in function would be something that let's say plus, okay, it's built-in. See, it's black plus 3 and 5. Okay, 3 and 5 is 8 because it's built in. Yeah. A user-defined function would be what we did last time. For example, funny plus. Okay, funny plus. Takes A and B is equal to A plus B and plus B plus the log of B. I don't know. I mean, this not going to make sense, okay? But you define it. You can make any definition you want, okay? You can make any definition you want. Now, obviously, it's not built-in, so it's blue. It's unknown. It's like a variable that's unknown, except it's the name of the function that's unknown. So you shift enter. Now it knows. So now you say, what is funny plus? Funny plus 3 and 5. It's not going to give you A. It's going to give you this. Okay. Now let's use another built-in function to turn this into numerical. Okay. So it's a funny plus, we define. So it's user defined. Yeah. I'm gonna revise this section a little bit later. Okay. So again, addition. Well, there's no point to do this, right? This is a repeat. The same thing as plus. So I'm not gonna do that. Okay. I just want to show that you can define. Now here's the thing that I want you to look at. A built-in function, right? 7 divided by 4. 7 divided by 4. Okay, 1.75. Okay. Now, what about 7 divided by 0? See? It's going to say infinity. It cannot do it. Now, in programming, when something gets stuck, sometimes you don't want it to be stuck. You just want to skip over it. Okay, I'm sorry, I shouldn't have done this. So instead of doing this, I can define my own divide function. My divide function check first if b is not equal to if Right. This is a little bit more complicated. Do this. If b is not equal to true, okay, return a plus b, a divided by b. Otherwise, produce this. Okay. So it checks. If a is not equal to 0, it gives me a divided by b. Sorry, if b is not equal to 0, it gives you this. Otherwise, it gives you a message. Okay, a message say cannot divide what? Divide a. Now a is a number, so I have to say let's make it into string by b. Cannot divide 1 by 0. ToString is a command for turning number into a string. It looks the same. So even if for built-in function, you might want to do this because you don't want the problem to stop and get stuck. Now you can do something like that. You know, I want to divide a by b. If it's doable, I divide. If it's not doable, I get a message and I move on. And I say something like, you know, maybe something like do something else, like ask for different b or something like that. Okay, so you can do that kind of thing in programming. So, right, power and root. Okay, so again, this is basic built-in. Power is exponential, right? So okay, good. A to the power b. Okay. Now root. I forgot how, there's always shorthand for this, by the way, but I keep forgetting. So 25, 5. Okay. Now you want to do the third root as well. For example, 125, third root is 5. Okay, that sort of thing. So you can see that the expression. So, all this log, sine, cosine, arcsine, all the arithmetic, all the trigonometric. Okay, ceiling and round, that's just like this, just rounding number. Ceiling just round up, floor is round down, something like that. Ceiling, 6. Now, what's nice about Mathematica is you can do this, by the way. Okay, let me do this. Let me do. If I get this, it's just round up to 6, right? Round up to 6. But I don't want to round up to 6. I want to round up to the nearest 0.25. Okay? See, the nearest 0.25 is that. Okay? Round down, floor. What do you think you get? This, right? So you can actually have this kind of rounding. So obviously, you know, when you work with money, the unit of denominator is cents, right? But we don't actually have cent, we have satang, and we don't have 1 satang, we have 25 satang. So you have to nearest, you have to do, you know, some kind of tax rounding or whatever, and you go to the nearest this. Okay, in bond market, it's really funny. Fixed income market is the nearest 132. Okay, so the nearest 132 is 183 over 32. Okay, it's really funny, but that's not conventional. So let's say, okay, let's say, let me show you what it is. Okay, so this is number. Yeah, so the nearest 132 is 5. Okay, so if this is 1 divided by 183, see, the nearest unit. Okay, so it's 183 units of 132. Okay, that's what for some reason that was the legacy of imperial system of numbers. Okay, like in the US, they use pound, they use whatever. So we use 1/2, 1/4, 1/8, 1/16, and 1/32. Exponential and logarithm. This is something you need to know. Okay. This is something you need to know. I want to show you something. Okay. And this is very interesting. Well, forget interesting. Let's make this real. Okay. You have 100 baht. Okay, you have 100 baht. You multiply by interest rate. Okay. Let's make the number general. Okay. Interest rate is equal to 5%. Yeah. 0.05. Okay. Your investment or your principal is the amount of money is 100 baht. Okay. Period is equal to 1 year. Okay. Period is 1 year. So principal, you end up with final or principal plus interest is equal to principal. Okay, now let's make this a function. Okay, let's make this a function. Okay, well, we don't have to make a function. Let's make this principal times 1 plus interest. Okay. Now, if you do this 2 years, what happened? You do this, right? So basically, you have to raise to the power of year. Okay, so to the power of period. Let's make it T. Okay, well, period. Let's say it's a year, T. Let's make it T. I think it's easier. Okay. So what do you think you're going to get? You're going to get 100 baht in the beginning, 5 baht at the end, 1 period. Correct? Okay. So now I'm going to make this a function. I'm going to make this a function. Okay. Let's call it PPI. Okay. Principal, interest, T. Okay, and then you do this. I just checked, I just did this. P, I, T. Okay, so see if this works. So PPI, 100 baht, 5.5%, 1 year. Good. So we got this. We need this. Now, let's do this. Let's do this. Okay, let's do this. Let's say that this is called annual interest. So let's say 2 years, right? Oh, sorry. This is wrong. The bracket should happen outside. Silly me. Okay. Now we didn't know this before because sorry. Yeah. TH should have spotted it. Okay. So there, you see? So basically it's 100 times 1.05 times 1.05. Okay. Now, let's say instead of this, you want to do semi-annual compounding. What does it mean? It means you, instead of getting 5% a year, you get 5% divided by 2, but you get it twice a year. Okay? So now, okay, Now notice the old number is 110.25. This new number is, oops. Oh, sorry. Okay, sorry. Okay, it's a little bit higher, right? It's greater than 110.25, right? Right? So what is better for the same interest rate? Do you want annual compounding or semi-annual compounding? You want semi-annual compounding, correct? Right? So let's put the number of compounding as a parameter. Let's do this. N is the number of compounding. So interest divided by N. Okay. Now, if you get half as much, you get twice as often. Okay. So let's do this. So now, by default, by the way, we can do this as well to say by default is 1. Okay. So by default is 1. But if I put in something like 2, get a different number. If I get 3, okay. So what do you think happened? Well, why don't we do this? We just plot this as a function of compounding. Okay. To 1000. Well, 365, let's say 2. Okay. 365 is daily compounding. I'm going to make it really big. Okay. Instead of, now I'm going to say instead of 10. Okay. So, right, what happened here is the number gets bigger, right? Gets bigger. What was it before? Okay, let's make one period. Okay, remember that 105. Okay, well, we can make it any period, doesn't matter. Okay. The point is that as you compound more often, okay, so this is let's do this. This is compound once, this is compound twice. You can think of it something as in between, as a sort of like a filling, like interpolate. So instead of compounding twice, you compound 1.4 times a year. Now, that's not very practical, okay? But the point is, you can fill in the number. So it gets bigger, but you want to be really greedy. You want to compound 1,000,000 times. Turns out that you will stop here, okay? The point is that this, okay, this value that it converges to is equal to 100 times this thing, this guy, this special guy, exponential. I can't find it. Okay, I don't know what the shortcut is, so let's go to here. E, okay? E, okay? To the power, e to the power, e to the power. Now, what's the interest? 0.05, okay? And how many years? That's 4. Okay, so this is basically this number here. So if you compound infinitely often, okay, remember this means that you get half the interest twice a year or quarter of the interest 4 times a year. This means you're getting 1,000,000th of an interest, but you compound it 1,000,000 times a year for that many years. Okay, This converges to exactly this. Okay. So that's why this is a very special number in finance. Okay. This is a very special number in finance. It's called Euler's. It's called Euler's number. Euler. Okay. It's this guy. Euler's E. Okay, we have to be a bit more specific because Euler did so many things. So let's say Euler's E. Euler's number, I think it's called Euler's number. Oh, Euler's constant. Sorry. Euler is like Gauss. No, use E instead. Okay, that's what we want. Okay, there it is. Okay. Euler is one of those guys where if you're not careful, it gives you different things because Euler did so many things. Well, that's that number. That's that number. Okay, it is a transcendental number. Well, that means a number that cannot be expressed as ratio as of integer. It goes on forever. So roughly speaking, it is 2.7183. Okay. Okay. If you remember this, that's good enough. Okay. The rest is goes on forever. So this is an exponential. Now, what's a logarithm?
อาจารย์ครับ
ครับผม
two questions from the chat two questions from the chat
Okay.
how reliable is the information from Wolfram Alpha for example
It's more reliable than Wikipedia because Wikipedia you can actually go and edit. Okay. In Wikipedia, you can actually go to and edit. So for a brief period of time before somebody catches up, you can write something nonsense. Okay. So you go to Wikipedia. Okay. Right. Okay. And literally you can go and edit. And you can say something like, whatever. Okay. So until somebody catches up, you can actually prank Wikipedia. Okay. Don't do it because Wikipedia will remember your IP address and you probably won't be able to access it later. Okay. But if you do something like with Tor or something, you can still prank Wikipedia. Now they have a way of getting around it. So Wikipedia can be pranked. Okay. You can definitely write silly stuff in here. Okay. Whereas this is a closed system, Wolfram Alpha here. So I think it's a closed system. So it's more reliable. You can't crank it. Okay. You won't be able to say Boolean is a basketball player or something like that. Okay. Good. Another question?
okay ครับ how can we open the basic math assistant tab like this one
Oh,
here?
sorry. If all the additional, but if you work with this long enough and and you have good memory better than mine, you have a lot of shortcuts. Okay, but if you don't remember, you go to palettes. Palettes is like in painting software, right? So you have palettes. So you have palette for special character. You have palette for math assistant. So that's basically the stuff. So most of the time, if you have math assistant, it has all the notation. Yeah, so you can do this. So this would be a to the power b. Now I think there's a shorthand. For some reason, I keep forgetting what it is. So I think it's a control plus or something. Okay, control arrow or something. No, not quite. A shift plus, no. A out plus, no. And this is where you actually have to go Google. Google is probably better for this. Mathematica, well, you can shortcut for raising our. Yeah, you go back to Mathematica reference, but the okay. Oh, control shift, control arrow, sorry. So if you want to say a to the power b, so a control, where is that little thing? B. Okay, so this is a shortcut. If you work with it a lot, you use this. But if you don't work with it a lot, you use this. So that's the thing. That's the okay. So there's palette for every. There's even a palette for this one. When I do presentations, say to clients or something like that, I turn this into PowerPoint. So I go to slideshow, and I show like a slideshow. So now I go to the next page and so forth. But so I can make this like a PowerPoint presentation. But when I work, I just have one continuous stream. So you can do this. You can insert page break, right? And then when this becomes a new page, okay. Right, fine. Now, so that's the exponentiation. Exponentiation is e to the power of whatever it is. So it's very useful in finance. Well, it turns out finance is a very tiny application. If you think about it, what is compounding? What's compounding? Is propagating the effect, right? What about you have contagion? Okay, one person affects. You have 10% probability of affecting 1% probability. So if you have 100 patients on day 1, you have 101 on day 2, and you have, right? So you can use this to model COVID. In fact, in my okay, in my COVID analytics, underneath is mathematical function, which at the end of the day is an exponential. It involves exponential, okay? Because if you think about it, well, forget about thinking about it, you probably hear things like exponential explosion or exponential contagion, right? Well, that's the same E. That's the E they're talking about when you hear the news. COVID, when you hear things like COVID is our pandemic is spreading at exponential rate. Okay, at exponential rate, it doesn't mean E is a number and you multiply. It's not. It's E to the power something. This exponential is this, and it is this guy. Okay, it's Euler's constant. Okay, so. Now this is something that's a bit more involved if you want to get involved. Okay, so Wolfram Alpha is, especially for numerical, it's curated. So in other words, they don't allow anybody to just go in and edit. Okay, you can't just say go in and make this number 12 or something like that. It doesn't allow. It's a closed system. Okay, now. Let's get to something that I think will be a topic that is very important. Okay. Binomial expansion. Binomial expansion. Now let me start with something else. Well, not something else. You've done this in mathematics, right? A, B plus C right? If you want to expand it, you get this, right? Okay. Now, likewise, if you do this, right? So A times B plus A times C, B times D plus C times D. Now, what if you want to do two terms in the front as well as in the back? So you do this: A plus B and C plus D, right? And expand it, right? How does this work? How does this work? Well, the way it works is front, 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 back, back, front, back, back, right? And you can keep going. Right? So front, 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 back, front, back, front, front, back, front, back. Okay, and you can keep going. You can keep all the combination, Now, this is just multiplication. Now, binomial expansion means that there are two terms. In this case, one term, two terms. Binomials means multiplying with itself 2 times. Okay, and you can do this more, 4 times. Okay, you can do this more 4 times. And this is something that you will see later a lot. Okay, so basically you just raise the power, but instead of a to the what's it called? Control shift, control arrow. 4. You're done. You have A plus B to the power of 4. Okay. Now, when you expand, obviously, what happened? What has to happen? We have front, 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 back, 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 front, front, back. So you can choose front or back. Okay? You can choose front or back, you can choose front or back, you can choose front or back. Right? So each term corresponds to that combination. In this case, A, and A comes over here. B comes over here. Now watch carefully. Watch carefully. What about A, B? Where does it go? It goes here. However, if you notice, A, B is the same thing as A, B, A. It's the same thing as A, B, A. It's the same thing as B, A. So there are 4 different ways. Watch this. 4 different ways of gathering 3 A's and 1 B. Okay? 4 different ways of gathering 3 A's and 1 B. So let's just say that I keep adding. Okay, keep gathering A's and B's. Now, how many ways of gathering 2 A's and 2 B's? There'll be 6. There'll be 6. It turns out that there is a pattern to it. If you're going to get pure A, there's only 1 way. If you're going to get pure B, there's only 1 way. You're going to get one mix. Okay, in other words, if you have 4, right? Instead of getting pure A, you introduce 1 B. You can do it how many ways? 4 ways, because you can do it here, 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 here. So you always have 4 over here. Likewise, if you work backward from B side, you can get there's only one way of getting all B's from 4 terms. But there's 4 ways of getting 3 B's and 1 A. And something more complicated in the middle. But if you notice, okay? If I do this, say 11, okay? It's gonna get messy. But guess what? There's only one way of getting 11 A's. There's 11 A's, 11 ways of getting 10 A's and 1 B. Going to the back, you're gonna get this. There's only one way. Oops, I don't know why this comes up. There's only one way of getting all B's. There's 11 ways of getting 10 B's mixed with 1 A. Now, something in here gets a little bit messy. Okay, it's a little bit messy. But at least you can notice something. You notice this pattern. And by the way, it goes forward and backward, very symmetric. 1, 11, 55, 1, 11, 55, 165, 165, 330, 330, 462, 462. Okay. So if you think of this, A as going left, B as going right, these are sort of like how many ways can you take 11 of them? How many ways? Like left, right, right, left, left, right, right, left, with 5 left, 6 right. How many ways are there? 162 ways. And this is something so useful that it has been uncovered many times over. In fact, there are 4 ways. Okay. Western way is called Pascal. The guy who came up with the way of doing this is named Pascal. Okay. So now in this case, I think I'll go to Google to show you history of Pascal triangle. Good. If you do this, you will find that there are 4 different histories. There is 17th century French mathematician named Pascal. Chinese mathematician names this. There's also Hindu and Arabic mathematician, 13th and 11th century. Let me see. There should be 4 different histories. In other words, it was invented 4 different times. So Chinese did it first, I think. Chinese did it in 1303. Okay, let me see. Chinese. There should be 4 people. There should be 4 people. So Chinese, Indian, Arab, and finally French. Okay, we call it Pascal's triangle. Oh, sorry. Even in Italy, there's another guy. So there are at least 5 different inventions of this. Now, what does it look like? It's that pattern. This pattern is called binomial expansion, and Mathematica use it so much that they built in this function called binomial expansion. By the way, so this is 1, 1, 1, 1, 2, 1. So this is I didn't arrange it very nicely, but I think Pascal triangle in yeah, it's nicer. Okay, let's get a nice picture of this. Okay. Right, Pascal triangle, you should have bunch of 1, and then you say left or right. Left, left, so that's 1, 1, 1, 1, 1, 1, 1, 1. So that's like going all A's. This is like going all B's. And if I want to go 1A, 1B, how do I do it? I can go A and then B, or I can go B and A. This counts how many ways, because this is 1 way, this is always 1 way. 1 way plus 1 way is 2 way. How many ways can you get to this? So all this triangle is giving you counting the number of ways you get to here. How many ways you can get from here to here? Now remember, you can't get a big jump. You can only go left and right. You can go left, 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 right, 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 right. You can go left, right, left, right, left, right, right. You can go right, 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 left, left, left. You can go right, 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 left, right, left, left. There are 35 ways. How do you know that? Because there are 20 ways getting here, 30 ways, 15 ways getting here. So 20 plus 15, 35 ways getting here. How do you know there's only 20 ways getting here? Because you get 10 ways of getting here, 10 ways of getting here. 10 plus 10 is 20. So you work backward. So this is Pascal's triangle. Okay, that's why if you have, okay, let's go back to our problem. Okay, let me go 1, 2, 3, 4, 5, 6, 7. Okay, let's go to 7. Let's go to this guy and make it 7. Okay, one way of getting all A's. One way of getting all A's. 7 ways of getting 6A, A, and 1B. 21 ways of getting 5 A's, A, 2B, or BB, A, or any combination. So basically, these are the different ways. These are the coefficients. Okay. Now, why do I care so much? Well, first of all, the fact that it has been discovered independently by 5 mathematicians at least that we know of, independently in hundreds of years, means it's very useful for something. By the way, I can do this. This is this is numerical number. So I'm giving a numerical expansion. Okay. So instead of now, here's an interesting thing. Okay. Let me just tell you, okay, that these numbers, as it gets bigger, it forms a pattern. There are, let me go back. The reason you have to know binomial expansion or Pascal triangle is because of 2 things. One, you want to know this second row. You want to know this. Second thing you want to know is you want to know this number. This will form a pattern. Now you don't have to know what it is yet, but I will show you. Basically, I use manipulate. You remember that, right? So this is 1, 2, 1. 1, 2, 1. Yeah. This is 1, 3, 3, 1. 1, 3, 3, 1. Let's make this 7. This is 1, 7, 21, 35, 35. 1, 7, 21, 35, 35. Now, as you keep going, it looks smoother. Okay? Anybody want to guess what happened? It's going to look this kind of shape. And this kind of shape will approach what's called normal distribution. Yeah? It's related. But so I want you to remember, at the very least, remember 2 things. If you go down 8 steps, you see number 8 over here. Say, 1 step, you see number 1. 2 steps, you see number 2. Okay? Remember this. And remember that this number, as you go down, it keeps going to that bell shape. It keeps going to that bell shape. Okay, see that bell shape. Now, let me stop there and say, now you have all the basic tools. Okay. Now let me just. So right now, you have deep insight. You don't have just a basic tool. You have deeper insight into what they are. But definitely, you have numbers. what you can do with numbers. You have sets. What you can do with sets. You have, what else? You have logic. You have Boolean logic. Yeah, that you can play with. What else can you do? Okay, you know that numbers, okay, you can use variable to represent unknown number. You can use function to represent a way of producing one number from another. Well, in real life, you may not just produce one number, and you may not just get from one number, you may be another from others. Okay? You can think of it this way, right? And you can play with that, and then you have basic number, like counting, and that's your integer. You have something for measurement, right? And then you have something like real number, right? Real number with decimal and whatnot, right? And then you have, so the function is way of producing one number from the other. Provide, so for producing, I'm going to change the word to producing input, output from input. Provided input value, right? Remember, you can divide by 0, something like that. Okay, and then you have some kind of basic function. Now, in high school, you probably have trigonometric as well, you know, like sine, cosine, tan, and those are useful, but I'm not covering them here. Okay, the one that I asked you to cover is exponential and logarithm. Okay, now logarithm is kind of the inverse of exponential, but I haven't talked about it yet. But we'll get to it. We'll get to it. We'll get to it. So exponential, okay. So exponential is like e to the power something is equal to the result. Okay, log is like you take that result equal to this. Okay, so this is not a real number. I'm not making it up. So exponential 1, 2, 3 is equal to okay. So this one. Now, if I take the log of this one, I get 1, 2, 3. So it's kind of like inverse of one another. Okay. So if you think about it, it's like exponential. Okay, exponential. We have 100 baht, and then exponential, and then interest is equal to principal plus interest. Okay, but a log function would be something like give you this is the end game. This is what you want. How much of an interest do you need? Okay, so it's kind of inverse. How much interest? So exponential say you have to do the interest and how long will give you the final amount. Logarithms say, well, if this is your final amount and this is your initial amount, how much of an interest and how long do you need? So it's inverse. So you know this basic. So, and one thing, and this is a binomial theorem. Now the reason it's called binomial theorem is because there's a way of calculating this individual number. You don't just do it by writing all this. You don't do this. There's a formula for this. So binomial theorem, okay, binomial theorem is actually a formula, gives you a formula of okay, of how to calculate this. And basically, that's what it comes down to. It's a whole bunch of combinatorial. I may get to explain this to you later, but not now, not now. I want to spend the last few minutes on this thing called visualization. Okay, so we saw a little bit of that already. Okay, we saw a little bit of that. So let's say I plot sine of x, okay, of x between state I minus 2 pi. Well, let's say from 0 to 2 pi. Okay, this is my function, right? Now, what if I want to plot 2D function? Okay, 2D function. By the way, let's make this okay, well, let's make it 5. Okay. Now, what if I want to make this a function of y? Well, obviously, this is function of y. It's going to look the same thing, right? Right? Now, imagine that this is the function of x plus y. How do I do that? Well, let's see if we can do that. Now, I can't do this. I'll show you. It's going to be an error. I can't do this. It doesn't work. But I want to plot 3D. So the command is 3D. Now I can do that. Now I can do that. Okay? Now, obviously, it's more interesting if I play with it. So let's manipulate multiplier. Let's call this a multiplier. N. Okay. Now, I'm going to use the same kind of thing, right? Except the same kind of format, which is curly bracket N, okay, going to from 1 to 10. Now, if I did this, Mathematica is going to interpret it this way. N is a continuous number, so I can put 1.2. Okay, so it's going to be like this. But if I want it to be integer, 1 to 10 instead of 1. Okay. Now, when I move, it's going to move 1 at a time. So it's 2, 3, 4, 5. Okay. Let's go to minus 2 pi. Okay, so 0, 0 is somewhere here, right? So you can see that as x gets bigger, you get the sine wave. As y gets bigger, you get the sine wave. As this line here is a line of constant x plus y, right? So it has the same value here because whether or not x is equal to this and y is equal to 0, or y is equal to this and x is equal to 0, or x plus y is equal to some constant, the sine function works the same. So if you look along the diagonal plane like this, it's the same value, right? So this is an axis, a different axis. Now, let's say I want this axis to move twice as big in x. I can do that well, but you know that's just cheating. Okay. But anyway, let's go back to this. So you can see that I can visualize, right? Now, what if I want to do this? What if I want to say, you know, let's make something that radiates from the middle. So how about, let's try this. Uh-oh. See? I get something really strange. It is a sine wave, but it's a sine wave that is constant on x times y. Okay, what else? What about distance from circle? Distance from origin. What's the distance from origin? What's the distance from source? It is square root x over to the power 2 plus y 2, right? So this is what I want to do. And guess what? I get a circle. Okay? I get a circle. Now, it gets more complicated because it's higher frequency. Okay? So maybe I don't have to go that far. Right? So you can make a donut out of this. Okay? Once you did this, you can, well, you can do two things. You can make this your 3D logo, and if you want to make a corporate gift, you can export it to a 3D printer and make a 3D printer print this. So that's your gift. So you are fine. I don't know, just to be fun. So that's visualizing a function of two variables. Now, two-dimensional parametric function, I'm not going to cover yet, but I have to, not yet anyway. Okay. The thing that we didn't finish a little bit is called sequence and series, but that's okay. I can come back and cover that in the linear algebra. So we are lacking a little bit in terms of schedule, okay, but we'll get there. We'll get there. I'm pretty sure. Okay, this is the first time I'm teaching the pre-course with Mathematica, so you know I have to adjust the time a little bit, but this will all be covered. Okay, so that's that. So we run out of time. We've done quite a bit today. Now this visualization, by the way, if you go plot 3D works on function. But if you want to plot data, it's called list plot. Okay, when you want, but you can do this. Just go to, just write list plot or list plot 3D, and on that word, just put in F1. And it's going to give you this. So instead of input the function, it's going to put a whole bunch of points, right? So for example, instead of having this, I say, I want to list plot 0 and 0 and 0, 1 and 0 and 7. Oops, sorry. Oops. Zero. Okay, so those are 2 points. 0, 0. So let's add another point to make it more interesting. 2, 3, and 4. Okay, so all these points are plotted. Okay, now if you want to link them, see the option, go down here, details and option. Now it's hard to see the point, so maybe you want so these are all the options. Okay, some options. Right. So for example, you can join, right? Join. So I can say, now this is the option is put in here as well. So you say join is true. Okay, the option is not put as an argument. Say join is equal to true. So let's go from 0 to 0 to this to this. Now notice it's not a function because it goes back, right? It goes back here and back here. Likewise, you can do list plot 3D. I don't know what it's going to look like. Oh, it can't. For some reason it doesn't allow to. Oh, what time you join? Oh, okay. Because when you do list plot, it's already on surface. So, you know, it's not very clear. It's not very nice example. Sorry. So you have other options. So F1 mesh. You can say something like, oh yeah, you can do something like this. So by default, it's giving this. It's called mesh. So I make it, I turn off the mesh. I don't interpolate and make it different colors. So this is, you know, all kind of stuff. You can explore this. So it's the same data point. You can make all kind of fun stuff. What you can also do is generate. Now, the last thing I want to do is this thing. I'm going to repeat next class. It's a very powerful function. Okay, it's called table. Now remember, I want to generate it. I want to say 1, 2, 1, 3, 5, 7, right? Now this is manual. I don't want to do this. What I want to do is I want to generate a list. Table of what? 1 plus 2k. K from 0 to 3. So what this is going to do is exactly that. So the table is going to generate this. So if this were like a real class with, you know, with problem, what I might ask you to do is create a table of sign and then plot it. Okay, so you can use plot. You can plot the sign. Okay, something. Or you can generate table of sign, something, and then list plot, and it will look similar. Okay, this is more precise because it's mathematical object. This is enumerating different point and then list plot. So that would be a good exercise. Okay, so with that, I think we've done enough for the day. Okay, let me make sure I don't save. Okay, so when in doubt, you know, just search and the command. And you know, the trick with Mathematica is if you don't know anything and you think it's a built-in function, okay, just key it in. If it's black and it makes a suggestion, then it's a built-in function. For example, logarithm. See, it's making all the suggestions. There's a log, there's a logarithm. So all these are built-in functions. So certainly, if you want to say LOV, okay, it doesn't make a suggestion, so you have to define. Okay, but if it comes up, then it's making a suggestion, all kind of stuff. So it's listing all kind of functions that begins with LO. So if sometimes you don't even have to, you just make a guess of what the function name is called. Okay, with that, I think it's good enough. Okay, the TA. Now, if you have any question or whatever, you can also consult with the TA. I think I have the TA put in their signature or their line ID. Okay, so with that, so let's end this lecture. Okay, I'll see you on Friday. See you on Friday.